So we have our first application, which is the pendulum. So this body, first we are required to show that it exhibits simple harmonic motion. And always the first thing to do when you are requested to show that a body is exhibiting simple harmonic motion is to find the source of restoring force in the motion of the body. So if you get the restoring force, then the next step is to just prove that force, which indirectly is acceleration, is direct proportional and opposite to the displacement. So we can imagine that this is a pendulum. Okay, this is a pendulum. This is the plane where the pendulum is attached, and this is the string. Attached is a body, a bob. Okay, pendulum bob is attached in the end. So if we look at this body, so it has weight that is acting perpendicular to it, and if I can magnify what is here, is that we have the weight acting downwards, we have the string that goes there, this is the body. Okay, so here there is an angle theta. Okay, and you have another component going there, of which this is the curve where the body is oscillating. Okay, yes, so this is the tangential force that is actually oscillating with the mass that way. So this is the weight mg, okay, because the weight is acting downwards. So the weight gives two components if we resolve the vector. Okay, if you remember in my series of lessons kwenye Newton's laws, I simplified it for you. If you are resolving away from the angle, away from this angle, inakuwa ni sin mg sin theta. If you are resolving across, you're taking it across the angle, inakuwa cos mg cos theta. So as you can see, this is the body that is oscillating maximum, inakuja to the mean, inaenda maximum, inakuja to the mean, inaenda maximum, inakuja to the mean. So all the time this component F1, which is mg sin theta, is the one that is pushing the body back towards the center. So that is our restoring force. And so that means this F1, which is the mg sin theta, is the one that is acting towards the equilibrium point. And so we have our restoring force. We have our restoring force that is acting towards the main, ambao ni mg sin theta. So tumesema for small angles sin theta is almost equal to theta itself. So badala ya mg sin theta inakuwa ni mg theta. But we know kwamba arc, if we have this arc, let us say this is y, the arc is y, and we have our angle here and the radius. So we know y over r is sawa na theta. So the arc length y is sawa na r times theta, and that means that we have our arc length y ni sawa na radius. This is the radius. For this case is the length of the string, okay, so the length of the string times theta. And so if we equate the two equations, we substitute theta with this formula. So from here we have theta is equal to y over the radius, for this case is the length of string. So if kwenye theta tukisubstitute y over the length, the aim is to get displacement ili compare na acceleration to see is it simple harmonic motion. So we substitute theta, y is equal to L, so tunakuwa na F1 is equal to negative mg theta is y over L. So here is y over L. So we have F1 is also negative mgy over L, where y is the displacement. As you can see, the body is moving maximum to the right, to the left maximum, to the right, to the left maximum, and each time the distance y is the one that is changing. That's the displacement. And therefore, if you can see clearly that mg, the mass is constant, the gravity is constant, and the length of string is constant. Therefore, F1 is sawa na k times y. K is the constant. The only thing that is changing here is y. So from Newton's second law of motion, force is sawa na mass times acceleration. So if we equate mass times acceleration is equal to negative mg y over L. As we said earlier, mass na mass, of course, they will cancel. Utabaki na acceleration sawa negative gy over L. G is a constant, length is a constant. So utabaki na acceleration is direct proportional to negative y, of which, as we said, negative signifies that the direction of the acceleration and displacement are in opposite direction. And so if this is happening, it means from mathematics principles, it proves to us that pendulum, when made to move in small angles, the body, the pendulum oscillates as a simple harmonic motion. So if we compare standard simple harmonic equation, okay, so we know acceleration is equal to negative w squared y. Okay, that this we know, remember the formula of acceleration in simple harmonic motion. And so here we have acceleration is equal to negative g y over L. So if we compare acceleration and acceleration, y and y, so we have w squared is sawa na gl. So it means when you simple harmonic motion, w squared is equal to gravity over length. And so if we find the square root both sides, square root both sides, square root of w squared and w is sawa na square root of gl. So we know that angular velocity is sawa na 2 pi over time period is equal to square root of g over L. So time period from this is sawa na 2 pi length of a gravity. This is a very common formula in your practicals. So this is where it is coming from. Okay, this is where it is coming from. If you decide to put it in terms of frequency, then it changes the whole picture. Okay, you know that frequency is 1 over time period, so you reverse everything. But this so far is most important to understand. So if we recall our principles of circular motion, we know what we call centripetal force, right? Is the force that is pulling the body towards the center of the cycle. So if this pendulum is moving, okay, if this pendulum is moving, remember this is like a half cycle. So if it were to go into a cycle, ingeendelea kwenda huko, ingeendelea kwenda huko, ingeenda huko, ingekuja kutokea huko. It means this could be a cycle. So this is the center of the cycle. So there is always a force that is pushing. Restoring force is pushing the body towards the mean. Centripetal force is pushing a body in circular motion towards the center. And we know that centripetal force is given by mass times velocity squared times r. Well, you can see this kwenye vipindi vya circular motion. The aim here is to just try to relate simple harmonic motion and circular motion. Now, how do they relate? So we know the net force acting kwenye string is what we call the centripetal force. Kwa sababu hapa kuna force mbili. Kuna force ya tension ya string ina act towards the center, na kuna force, kumbuka tuliresolve hii component ya mg cos theta, ina act away from the string. So you can see mg cos theta ina act, tension ina act in the opposite direction. It means the difference between the two forces, because they are opposite, is what itakuwa ni centripetal force. So you have the tension minus the horizontal, the vertical component of the weight, tunapata centripetal force. So if you take the tension minus F2, for this case is the mg cos theta, tunapata sasa na centripetal force. So tension ya kwenye string is equal to mv squared over r plus F2. So mv squared, okay, of the radius is the length of the string. As I said, that if this is a cycle, the radius itakuwa ndo urefu wa hii string hapa, urefu wa hii kamba. So as you can see, MVL plus mg cos theta. So hii ni basic concept, as we shall see hapo mbele. We might require to use this knowledge kwenye kufanya maswali. Sometimes they proceed further kukuuliza find the tension kwenye hiyo string, but more of this you'll find it kwenye circular motion. I hope everything is clear kuhusu pendulum, how we have derived. Cha muhimu hapo ni kujua how we have derived the equation of the pendulum and the time period and finally the tension. So make sure you understand clearly how we have proved that a pendulum is exhibiting simple harmonic motion. It is another common question.